I would like to give the mic to Rhodri Cusack from Trinity College Dublin to lead the symposium.
Thank you very much. So I'm Rhodri Cusack. My co-chair, Moira Dillion, is just from NYU, is just attending online. So I'm really excited to be here for this first symposium of the conference. Now we know that computers can learn abstract things, but they are still doing it babies do it much, much better. They do it with much less data, and they do it much more energy efficiently. So there's still something, there's potentially that machine learning can take from developmental science. And in turn, we can use the computational models from machine learning, provide fantastic models that developmental scientists can use to come up with more concrete and more specific ways to understand how babies learn, so to really inspire our science. Now, to make these things happen, we're going to need an interdisciplinary dialogue. So I'm really excited to be introducing today our 4 speakers who are all working at this interface between machine learning and infant development. So without further ado, I'd like to welcome our first speaker, who is Shannon Yasuda from NYU.
Hello, everyone. Can everyone hear me? Okay, great. So my name is Shannon Yasuda. Our planned presenter, Moira Dillion, was unfortunately unable to join us in person, but I'm very pleased to present to you today our team's work. Artificial intelligence promises to take the flawed intelligence of humans out of machines. Why then might we want to put the early intelligence of human infants into machines? The work I'll tell you about today at the intersection of the developmental, cognitive, and computational sciences suggests that infants have a lot to teach machines and will help them learn better. For example, while infants seem to have a rich, common sense capacity to infer others' goals and preferences merely by observing their actions, AI systems, in contrast, typically favor direct behavioral predictions. This leads to AI that falls short in addressing novel, but common sense interactions in the social world. These failures are striking compared to infant successes. For example, here is an infant who has clearly inferred the goals of his canine friend, and he's helping his friend achieve that goal. And here's a robot attempting to complete the same task.
I've got it. I'll use my sonars to take a walk and explore my environment.
If an aim of AI is to build the flexible, common sense thinker that human adults become, then machines might need to start from the same core abilities as infants, whether achieved through learning-based or engineered approaches. Nevertheless, comprehensively characterizing infants' knowledge is difficult, as behavioral experiments with infants typically focus on just 1 or 2 abilities in one content area, rely on diverse materials and methods, for example, live actors versus animations, and are presented to different groups of infants. And so here's where 2 goals from 2 different fields align. On the artificial intelligence side, the goal for the work I'll present today is to compare infants' common sense knowledge to machines with the aim of revealing essential ingredients that might be missing in existing models of common sense AI. On the developmental psychology side, it is to make a comprehensive framework in which to test infants' understanding of the intentions underlying agents' actions. To meet these aims, our team designed a suite of tasks called the Baby Intuitions Benchmark, or BIB, which challenges both infants and machines to reason about the underlying causes of observed agents' actions. We recently published BIB as a machine learning benchmark in NeurIPS, shown here on the left, and today I'll focus on infants' performance on BIB and the comparison between the performance of infants and the performance of 3 strong baseline computational models. To read more about this work, you can check out our preprint shown here on the right. BIB includes short, silent, animated videos with simple visuals, like those used in these seminal displays of Hyder and Simmel, including basic shapes without eyes or limbs, undertaking basic movements in a grid world. These displays challenge the limits of an observer's inferential capacity and reflect the kind of abstract knowledge that infants are thought to possess. BIB's task structure adopts a violation of expectation looking time paradigm often used to test infants, which includes a series of familiarization events that serve to set up an expectation, followed by test events in either order, an expected outcome that is perceptually dissimilar to the familiarization but is conceptually consistent, and an unexpected outcome that is perceptually similar to the familiarization but is conceptually surprising. If infants form the correct high-level expectation, they will look longer at the unexpected versus expected outcome. Shown here on the screen is an example of BIB's goal-directed task. During familiarization, the clover moves consistently to the Rouleau triangle across 8 familiarization trials, which differ slightly in the location of the 2 objects across trials. At test, the location of the 2 objects switch. If an observer generally expects agents to have object-based goals, not location-based goals, then they should expect that the clover will continue to move to the Rouleau triangle, even in its new location. An observer should find it unexpected, in contrast, for the agent to take a path it took before, but this time to a new object. This task structure has been used in recent machine learning benchmarks, focusing on common sense, and is advantageous because it both protects against low-level heuristic-based solutions and allows for an algorithm's quantitative measure of surprise to be compared to a well-established psychological measure of surprise, infants' looking time. Here's a very brief summary of BIB's suite of 6 tasks. We have 3 tasks focusing on expectations about agents' goal-directed actions, 1 asking whether those goals should be objects or locations, as I just reviewed, another asking whether goals should be shared across agents, and a 3rd asking whether new goals should be formed when previous goals become unattainable. We have 2 tasks focusing on expectations about rationally efficient actions. 1 asking whether agents who have previously moved efficiently around obstacles to an object will continue to do so when the environment has changed. And the other asking whether agents who have previously moved inefficiently around obstacles to an object will now move efficiently for the first time when the environment has changed. Finally, we have 1 task on expectations about instrumental actions, asking whether agents should only take instrumental actions when those actions are necessary. With nearly 300 Zoom sessions, we tested 11-month-old infants on BIB's entire suite of 6 tasks. Here's an infant participating in the efficient agent task. So you're going to see 1 of 8 familiarization trials in which the orange pill is moving around an obstacle in the environment to its goal object, the blue bottle. Now you'll see the 2 test trials, starting with the unexpected trial. The obstacles have changed. The pill takes the same path it took before, but now that path is inefficient. The infant is surprised and looks a long time. In the expected outcome, it'll be an entirely new path the infant hasn't seen before. But it's conceptually consistent insofar as the orange pill is moving efficiently to its goal object. The infant doesn't look very long. We also tested 3 learning-driven neural network models on the same trials that infants saw. These models span 2 classes: behavioral cloning, which is meant to predict the next action of an agent, and video modeling, which is meant to predict the next frame of a video. Within the behavioral cloning model class, we included 2 different ways in which the familiarization trials were encoded. All 3 models were designed to form implicit mental state inferences from observed behavior. Prior to being tested, the models were trained on BIB's background training videos. At test, the models formed predictions about an agent's actions based on its actions during familiarization. To obtain a continuous measure of surprise as a correlate of infants' looking time, we calculated the model's prediction error for each frame of each outcome and considered the frame with the maximum error. I'd be happy to go into more detail about the models in the Q&A. So how did infants and models do overall on BIB? What I'm showing here are z-scores of infants' looking time in red, and the 3 model surprisal scores, each model shown in different shades of gray. The 3 tasks displayed here on the left are the ones in which infants demonstrated consistent action understanding. About goal attribution and rationality attribution, showing greater surprise, which is to say longer looking, to the unexpected versus expected outcomes. The goal attribution task shows that infants expect agents to have object-based goals. Infants are surprised, they look longer, when agents move to a new object at test. The rationality attribution tasks show that infants expect agents to move efficiently to objects that after environments have changed, regardless of whether they had previously moved efficiently or inefficiently. In 2 out of 3 of these tasks, the models show nearly orthogonal performance to infants. Models expect location-based goals, not object-based goals, or have no relative expectation here, and models only attribute rationality to previously efficient agents. They do not extend their rationality attribution to previously inefficient agents. Finally, the 3 tasks on the right, where infants had no consistent predictions about the goals of new agents, about agents' goals when previous goals become unattainable, and about novel instrumental actions, models showed no additional common sense psychology. I'd be happy to talk more about the results of these tasks, including what look like model successes but aren't, in the Q&A. Overall, infant successes on BIB suggest they have a highly abstract notion of agents' actions as goal-directed towards objects, and a principle of rationality that leads to default expectations of agents' efficient actions towards goals. These results are consistent with the rich literature on infants' common sense psychology and synthesize the literature's findings in a unified framework that can be directly compared with and perhaps built into machine intelligence. I'm happy to go into more detail about what might be behind infants' failures on some of BIB's tasks in the Q&A. In short, we believe some of these failures could suggest that changes to the contexts in which goals are first demonstrated may have significant impacts on infants' goal and rationality attribution. For example, consistent with the findings of Somerville and Crane, infants may not generalize an agent's goals to a test environment with any changes, even minimal or inconsequential changes, relative to the environment in which the goal was initially demonstrated. In our case, like changes in the arrangement of the black obstacles in the grid world. Here on the left, we have BIB's original goal-directed task, which infants succeeded on, and on the right, we have a potential new version of the task in which we introduce obstacles during familiarization. This introduction may actually boost infants' performance since there will be more cues to the clover being an agent. But then, if we change the arrangement of the obstacles at test, that change to the arrangement of the obstacles may wind up wiping out any initial goal attributions. Environmental changes like these, from familiarization to test, were present in BIB's other goal-directed tasks in which infants failed, but those tasks also had other changes relative to this original goal-directed task. We did not originally design BIB to examine the effects of such environmental changes directly, so we plan to follow up. Regardless of how infants come to understand this geometry of BIB's environment, their sensitivity to and use of where an agent is for goal and rationality attribution seems apparent. Future studies might thus investigate infants' use of such geometry for recognizing places based on their shape or navigability, even before infants can navigate on their own. Future work exploring infants' knowledge about the world could also extend our general approach to investigate other aspects of infant common sense psychology. Because BIB's tasks are procedurally generated and presentationally consistent, for example, New tasks, like those I just described, focusing on environmental changes, could easily be incorporated into BIB's dataset. In addition, future studies using BIB's paradigm might explore other potential aspects of infants' common sense psychology, including examining the behavioral cues infants use to attribute agency to begin with, or the cues they use to recognize potential social partnerships between agents. For example, infants should only attribute goals to agents. They should not attribute goals to objects. And so in a new agency attribution task, for example, we are showing the orange circle here, either initiating its own motion around obstacles consistently to the green arrow, or being hit by a constantly rotating spinner, bouncing off a wall, and then landing at the green arrow. At test, the location of the two goal objects switch, just like in the original goal-directed task, and the contact or lack thereof with the spinner is occluded. Only in the case of the agent condition should an observer predict that the orange circle will move to the green arrow, its goal object, now in a new location. In the case of the object condition, there should be no relative expectation. In a new imitation task, the orange circle moves in the same way as either the green square or the blue rouleau triangle. In the social condition, this movement affects no change in the environment and serves no instrumental goal. In the instrumental condition, however, the orange circle's movement brings it into contact with the gray pentagon, which changes color and plays a noise upon contact. Only in the case of the social condition might an observer infer that the orange circle's movement is social. And so in that case alone, an observer might expect the circle to approach the green square, whom it previously imitated. There should be no expectation in the instrumental condition. While we show that learning-driven neural network models already fall short of infants' common sense on BIB's existing tasks, such social expectations will nevertheless become increasingly important for AI too, as it becomes further embedded in real-world multi-agent settings that demand common sense. Extending our approach can ultimately inform comprehensive accounts of infants' knowledge not only about agents, but also about objects and places, allowing us to more fully describe the origins and development of human common sense and provide an avenue for building the future of human-like AI. BIB called for an inter-animating research program between developmental cognitive science and artificial intelligence. The present work demonstrates that such a program is both possible and generative for both fields. Our work provides a first step in this productive dialogue among the developmental, cognitive, and computational sciences to test whether knowledge can be built in humans or machines from the foundations that our theories postulate. Thank you so much.
Oops. Sorry. Do we have any questions? Let's see at the back there. Any questions there?
Okay, I can ask one. Thank you so much for this wonderful talk. Something that I have wondered about for a while, and I think maybe you would be the expert to answer, is in the case where you see an agent going to a location, can infants and maybe machines eventually update that the agent actually isn't trying to get to an object, but they actually are trying to go to that location? So for example, let's say as an infant, you usually when your parent goes to open a cupboard, they're going to try to take something out of it, but let's say that today they're actually opening cupboards just to see what you have before you go shopping. Is that infant going to be equally surprised when cupboards 1 through 3 are opened as like cupboards 4 to 10 or whatever? Or can they start inferring that there's actually a different goal at play?
Yeah, I definitely think that's possible. I think that's something that's valuable about the goal-directed task is that it allows us to sort of see that perhaps infants' initial goal attribution is those of object-based goals, but it's still possible for there to be location-based goals. And so we actually have ideas for follow-up experiments involving efficient action. So one of the reasons that we think how infants might handle inefficient agents is not that they're being irrational, but maybe they just don't have object-based goals. Maybe they have like location-based goals or movement-based goals, which are actually even more similar to, for example, the imitation task, where the motions are social. They're not goal-directed towards a specific object. It actually has to do with the movement itself. So I definitely think that's something that can be explored using this stimuli. In particular, it's well suited for those types of experiments.
We've got time for one more question. Perhaps if the next speaker would like to come up and, Koleen, set up your computer. Well, was there one more? Sorry, I can't. Oh, just there.
Hi, thanks very much. Can you tell us a bit more about how those neural networks that you were comparing to were trained, and in particular what it is that they were trained on? What was the data that they were trained on?
Yeah, so we have several different background training sets, which are similar to our evaluation sets, but actually I could have shown them. I had a slide, but they involve. Yeah, let me just quickly show it because I think that would be helpful.
Sorry.
Let's see. So these are examples of our background training tasks. So some of them are no navigation preference training tasks. Some of them are navigation, but only to one object as opposed to a preference task. And some of them involve that green barrier, and which allows them to understand the instrumental task. But we have a few different versions of these background training tasks, and we create because of the way our stimuli is designed, we can procedurally generate tens of thousands of these, which we can use to train the models, and then we just use 80% to train, and then the other 20% to validate that before we actually test the models on our evaluation set, which is similar to what we use for the babies. The babies don't see the training set because we assume infants have a set of, they're trained and they already have a set of knowledge that the machines won't have coming in. But that's something that we've also thought about potentially adding in. Perhaps infants also need some sort of background training the way we have for machines for some of these tasks.
So do you think that the sensible question is to see what kind of battery of tasks you need to train the networks on so that they exhibit the same sort of common sense performance that babies do? Would that be a relevant question here?
Yes, that's definitely an important part of this this benchmark is also having that background training set. So for each task, we think of new background training that would help, especially in this context, that would allow the machines to better understand the task itself.
Great.
Yeah.
So let's thank Shannon again. Thank you very much. That's great. Thank you. So our next speaker is Koleen McCrink from Barnard College and Columbia University.
Okay, wonderful. I'm so happy to be here today. This conference was the last time I went to, the last one I went to before COVID shut the world down. So it's really, really nice signal. I'm going to be talking, in 1 minute I will be talking about some work that I've been doing lately on artificial intelligence, which is not normally in my wheelhouse, specifically on using developmental psychology theory and methods to evaluate artificial intelligence. And this work is happening with many other people, but what I'll be talking about today is in collaboration with Lisa Oakes and David Moore. And it is as part of the Machine Common Sense, or MCS program, that's being funded by DARPA, which is the research arm of the Department of Defense in the United States. And it has as its premise a now, relatively famous quote by Alan Turing over 70 years ago. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If it were then subjected to an appropriate course of education, one would obtain the adult brain. And this, probably as developmental psychologists, makes a lot of sense to us, right? We don't want a system that's rigid. We want a system that's flexible and can learn, because that will lead to sort of a greater sense of common sense. Now, I'm not developing the artificial intelligences in this program. That task falls to 3 different teams. These teams are called the Technical Area 1, or TA1s. They're the performers who are making the artificial intelligences. And it's a really beautiful blend of some really high-profile, very thoughtful developmental psychologists. People like Karen Adolph and Liz Spelke, Alison Gopnik, and all of the teams have combinations of developmental psychologists who are used to studying how systems develop, and AI engineers who are used to developing systems, right? So you can see how these fields would organically inform each other. Our role on TA2, or Technical Area 2, is as evaluators, which is to do a couple of things. The first is to determine exactly what sorts of tasks might fall under common sense, a rubric of common sense, developmentally speaking. The goal for the program is to get these artificial intelligences up to about 18 months of age, which was intended to be a relatively easy age target to hit, but for anyone who has children or who studies toddlers know they may have shot themselves in the foot a little bit by choosing the least sensible age ever. So we're trying to model essentially very early development and assess whether or not these systems have achieved it. So you can find more information about this program at machinecommonsense.com, and this also has a link to the GitHub page that has all of the technical materials that our engineering team has developed, as well as how to access things like the interactive learning environment, which I'll talk about more in a moment. So the structure of this, we had to make a very extensive table to sort of guide what we're going to be testing and what we're going to be evaluating the artificial intelligences on. And it was modeled after Liz Spelke's core domains of cognition: objects, agents, and places. And then once we have these domains, right, that we think machines will be able to garner information about, we're able to have a series of meetings at the start of the project that outline core principles that we think even very young children have within these domains. So things like objects have depth and they move in 3-dimensional space, or objects persist even when they're occluded, right? Very sort of straightforward principles where no matter your theoretical background, you can be like, yeah, that babies have, right? That's a principle that babies have. And once you've established what these principles are that a reasonable set of people can agree on, you can now set to the task of figuring out how to test them, how to get the artificial intelligence put through its paces. And we have 2 different sorts of tests, one that was inspired by Emmanuel Dupoux's IntPhys evaluation set, and one that was inspired by Lucy Checky and Jose Aurelio Hernandez's Animal Artificial Intelligence Olympics. Some of them are passive and require the artificial intelligence to generate a signal of plausibility, much like with violation of expectation paradigms that you use with infants. We use looking time. The AIs generate a plausibility signal. And the other sorts of tasks, which now comprise the majority of our evaluation sets, is actually they're interactive. So using machine learning, specifically reward learning, the AI is trained in retrieving a target from the environment, and I'll talk more about the training in a moment because it turns out to be a very interesting and important part of evaluating artificial intelligence that I don't think we appreciated fully before when we entered into this endeavor. So we have these two different sorts of tasks, and once you have a task, you can do what every psychologist has ever dreamed of. You know how when you say, if I had 1,000 babies, I would just test this, I'd test that. You can do that. They're computers. Go ahead, put them through their paces, run them 24 hours a day in the cloud. So we can go in and we can make what we call these experimental hypercubes, which are essentially just visualizations of multivariate experiments that have a bunch of minimal comparisons to see where the system succeeds or fails. So in this particular case, right, trying to assess recognition that objects don't appear or disappear behind occluders, we have a design that has 3 different hypercubes, and we're manipulating the way that the object is moving in the environment. Is it moving in depth? Is it being tossed onto the screen? Is it moving on a single plane of depth? We are manipulating whether or not there's occlusion that's taking place on the scene. We're manipulating whether or not we're showing a scene that's overall plausible to the AIs or overall implausible. We're manipulating whether or not the objects that they have to reason about in the scene are things that they've been exposed to before in the training environment, which is really important. And I'll talk about that more later, but this sense of generalization, I think, is one of the major players, I think, that most people can agree on that's underlying common sense. Right? If you see someone walk into a novel environment and handle it nimbly, that's the point at which where you're like, oh, that person has pretty good common sense. So generalizability is famously hard for artificial intelligences, but we really wanted to try and push that envelope in this evaluation program. Once you visualize the hypercubes, you can run the AIs through the evaluation pipeline and then determine where performance is weak or strong at a glance. So I go through and I color code all of the teams on all of the designs with either good performance, 75% plus, or poor performance, under 25%, or somewhere in between, right? And then you can actually go into a user interface that our engineers have developed and pull up trials where they're looking especially good or especially bad. And this will be guided by the visualizations of the hypercubes, right? You can look and see here, oh wow, it really seems like they're having a problem with plausible trials relative to implausible trials. It seems like they're doing worse when there's more occlusion in the scene. And then you can go up and pull various scenes like this one to occluders. A rolling duck toy comes out and doesn't appear between them but emerges on the other side. That's implausible. Relative to this one, which is yoked experimentally to the other one, where you see the object in between the two occluders. This particular AI system, which is the OPICS team, which is Oregon State and NYU, Karen Adolph and Alan Fern are the sort of respective leads for that. This team, their system is very sensitive. It's actually oversensitive to implausibility. So they tend to have what we're calling an implausibility bias. That's just one comparison of thousands that we've done so far. There are an absolute ton of experimental comparisons that we've been able to generate in this evaluation set. So I'm actually not going to talk about any sort of specific results for the remainder of the talk. I'm going to give you a sense of, wait, 5? I have 20 minutes, no? Oh God, okay. Okay, so first of all, definitions of common sense are extremely variable, right? And this really echoes the perception, cognition, interaction discussion that a lot of cognitive psychologists have. Where do you draw the line between low-level perception and high-level cognition? Well, it turns out You kind of can't. They inform each other, right? AI really brings us to the forefront because we ended up ultimately having to give the performers a lot of things that we take for granted as humans. I was going to say as developmental psychologists, but really as humans. Things like perceiving depth in the environment or segmenting objects. Low-level visual cognition is not artificial intelligence's strong suit. But it's really important to give to the systems in the current state of the art anyway, because if you don't, then it's like testing babies in a dark room. They're failing for the wrong reason. They don't even have the input. The other illuminating challenge is that it's really hard to know where to draw the line between what's a heuristic and what's an abstract principle. So in this particular situation, you can use logic to know how big the target or the soccer ball is to know not to go to the right side, right? If you're the artificial intelligence in this scenario. But perhaps you maybe want to use that what we would call a heuristic or a hack of always going to where on this right side here where the larger occluder is, which one of the teams did. Now, when we first saw this, we were like, oh, this is just a heuristic or a hack. But in conversation with the performers, I think what I started to realize is that a rich cognition has to be comprised of something, right? And maybe what we can do to bridge this still existent gap between nativists and empiricists is just frankly acknowledge that we may have a variety of heuristics and hacks that we've been exposed to through evolutionary time that has given rise to abstract principles, right? The next illuminating challenge, I have like 8 more, so we'll see what I get through, is that artificial intelligences are very, very slavish to their training. And we actually originally, when we started our evaluation, our part of the team, we were like, we're not gonna give them training. We're not gonna give them training. We're just gonna pop them in there in the evaluation, just like we bring babies into the lab and we don't give them any exposure. We'll see what they've learned. This was actually a tremendous technical problem and the teams hated it. And now I understand why. You have to give some sort of zeros and ones, some information about the environment. Now, what the performers really wanted is they wanted 100,000 extremely similar training sets to our evaluation tests. But we really stood firm, and I think for the future of artificial intelligence evaluation, it's important as an evaluator to be independent, right, to not be on the teams, but also to really be disciplined in the sort of training that you provide to them. And in this case, what we did is we provided something that we're calling the interactive learning environment. The engineers spent a ton of time making what essentially amounts to an artificial large playroom or small world for the artificial intelligences. So this particular playroom, they can do things like, this little R2-D2, by the way, is the artificial intelligence. It's the robot that's navigating the environment, the ILE. So there are many things in here. There's ramps, there's platforms, there are objects that can come down from the ceiling and become occluded. There's rotating cogs for things like spatial transposition tasks. So the interactive learning environment has been an incredibly large part of moving this project forward because we're able to provide an environment for the AIs to learn, but not give them tens of thousands of teach to the test training sets, which I think has really helped our performers create more robust AIs, which they were on their way to anyway, right? They knew this was a problem, but every time you provide a ton of background training, you're sort of enabling this teach to the test philosophy that you sometimes see with AI evaluations. In fact, that you see a lot with AI evaluations. We have very different machinery from computers, right? We get for free things like size constancy and depth perception as newborns. This is not an issue for us. But computers have a lot of things that we don't have. They have crazy processing speed, really nice memory. Kids famously bad at both of those things, right? There are also social cultural aspects to children that are key drivers to cognitive development that I did not fully appreciate before I took on this project. Things like inherent curiosity, a drive to explore, motivation, an appreciation for pedagogy, and understanding that other people are there to teach you things. That is very, very hard, right, to capture in an artificial intelligence. But those sort of large sociocultural frameworks are important drivers when it comes to guiding things like attention in the environment or what inputs you're going to take from the environment. Okay. I'm not going to show that. Okay. The next is that I'm actually not sure now, several years into this project, that expecting artificial intelligence and humans to solve things in the same way is necessarily the best path forward, right? There are a couple preconditions for this assumption, and one of them is that humans are computers and computers are humans. I'm not sure that's true in general, but even if it's true, we're not there yet, right? So I think ultimately whether or not you're going to focus on the means or the end, whether or not you're going to focus on the task getting accomplished or the way that it's being accomplished is going to depend on who you are as a funder, right? If you're DARPA, if you're thinking about really fraught situations where quick responses are needed, then you're not going to want to limit the systems that you're using or developing. You're going to want them to be fast and high information processing capacity. But if you're NSF, and you're interested in like the mind, not the brain, the mind, capital M, then you may want to go in and really sort of artificially deflate the capacities of the systems that are being built in order to better model development, in order to bring them more in line. And then finally, the last illuminating challenge was that we initially had actually a lot of pushback as evaluators, and we really had to take effort to create a relationship between the evaluation team and the performers. But it's been incredibly fruitful once we were able to realize the limitations of the current state of the art in artificial intelligence and work around them, but also create an evaluation that we hope is really helping the performers out by giving them information about their systems with these sort of really minimal comparison experimental designs. Usually if you are developing an artificial intelligence, if you're in that field, you're sort of submitting to these large-scale evaluation platforms and you get back a score, and that score goes on a leaderboard. It's pretty black box. But that type of evaluation that we're doing, where we're taking into account the background of the performers and what their AIs can or cannot do with readiness, I think there's been a lot of mutual respect that has evolved, and it's been much more informative to them. So we're really used to, as developmental psychologists, like threading the needle of what you can or can't do with the organism that you're studying. So between that and experimental psychology design principles, we're actually, I think, a perfect fit for AI evaluation because we can think about the constraints of the system. We've been doing that our whole careers, essentially. I'm sorry I went over time. Thank you very much. Usual disclaimer, and I'm part of a much larger team who's doing this. Thank you.
Thank you very much. We have time for one very quick question while the next speaker gets set up. Anybody has any questions? Don't be shy.
So, yeah, I think, can you hear me?
No.
Can you hear me now?
Yes.
Okay, yeah. So I have one question about like one kind of compromise that you discussed at some point.
Not on. Try.
Is okay now?
Yeah.
Yeah, cool. Okay. So at some point, so great talk, I really enjoyed and very interesting question. At some point, you pointed at a kind of compromise that you had considering as the evaluation team. There was the one of equating like an heuristic, like go to the large occluder with the, an inference like a ball cannot be hidden behind a tiny occluder. And I would, and of course, intuitively it seems that it might be an issue if what you are targeting is the flexibility and generality of people's common sense. And I was just curious whether you could defend more, elaborate on that decision that you are making as the evaluation team, if I understand, of equating that kind of inference with heuristics.
Right. So I was rushing. I apologize. The point I just wanted to make with that particular example is that as someone who really believes in rich cognition, this project has forced me to think about how you actually implement that in a system instead of just saying, it's a principle, right? Where are those principles derived from? I think now that I've been working on this, I suspect it is a principle that is derived from many, many sorts of heuristics, right? I think our abstract cognition, our principles, are 60 million years of heuristics, right? And that, I think AI lays really bare. Because when you're developing an AI, you need to be like, oh God, how am I? It's one thing to talk about an abstract principle, but programming it as an AI engineer, it's like, how am I going to build it in? And the answer is you build in 1,000 different ways of solving the problem that end up looking like something that's very rich. And maybe that is something that's very rich.
Great. Thanks very much. So the penultimate speaker today is Clíona O'Doherty from Trinity College Dublin.
Hi, everyone. You can hear me okay, yeah? Great. So it's great to be talking to you all today. My name's Clíona. I'm a PhD student with Rhodri. So we're an infant lab, but we also spend a lot of time thinking about artificial intelligence, how machines might learn, and kind of like how Rhodri mentioned, how we can actually use AI to help us learn about how infants learn. So today I'm going to touch on both of these topics and these fields, and also I'm going to present my specific research investigating how I think long temporal statistics that are just existent in the environment that an infant's exposed to could inform our understanding of the things we see. So we're interested in how infants develop, specifically in their first year of life. This is a time when human infants are really helpless. They're very dependent on their parents. This plot here just shows that humans, in comparison to other mammals and birds, are dependent on their parents for one of the longest periods of time. But then they go on to grow one of the largest brains in terms of number of neurons. So what if there's actually a link here? And maybe this period of helplessness is important for going on to develop that later intelligent behavior that we know and we see and was discussed in the other talks. But it's difficult to test this, especially as we get younger and younger. We have lots of amazing tools from developmental science, cognitive science, like we're all familiar with. But sometimes we want to look inside the brain. And today I'm going to talk more about the neuroscience side of things and looking at the brain. But we do have to get creative with the tools that we use. So some of the tools that we use in our lab, we look at computational modeling, testing learning mechanisms in computational models, and then seeing what different things we can learn from the environment. We want to relate back to brains and behavior, so we choose to explore these questions in the visual modality because vision is strongly linked to computational modeling in terms of neuroscience and computational modeling. Not only that though, but if we want to use the latest methods in neuroimaging to look inside infant brains, then visual paradigms are just really engaging. They give us one of our best shots of actually collecting successful data from infants. So we're thinking about how infants learn from their environment in the first year of life. So what is their environment actually like? Think about a baby who wakes up from their nap. Maybe they're awake for an hour or so or longer, and they might be in the kitchen or the living room. Maybe they go to the park if they go for a walk, and then they might fall asleep again. but they have this extended experience in a particular context. I think so anyway, when you just think about it. And from that context, there are going to be various statistical cues, co-occurrences, associations, all these types of statistical cues that we know can guide infant learning. So I wanted to check if infant environments actually were like this. Were they experiencing a particular context for an extended period of time? And so I quickly took the SACAM dataset, which is an amazing resource of headcam videos from infants. And I just took the videos from infants 12 months and younger, because we're looking at infants in the first year of life. And yes, it looks like the locations that they experienced were actually following this pattern. Within the videos, they tended to be in 1 and maybe 2 locations. And then also, despite them experiencing a large number of distinct locations, most of the time they actually were only in 1 or 2, including the living room, bedroom, maybe outside on their own property. So, an infant's experience from this quick check does seem to look something like this, like extended exposure to familiar environments. And from this, maybe they could be picking up on those statistical signals that exist on the longer timescale that you'd experience this environment for. Could they extract the co-occurrences and statistics and actually learn a better understanding of the place they are? So what I mean by this is not just recognize, oh, that's a sofa, but that the sofa tends to be in the room with the TV. Here's the place where we play, or we watch TV, or my parents watch TV. So they could pick up on these longer associations within a particular context. And just, I want to point to this study from the Yale lab, recent neuroimaging evidence that just says that infants actually do parse their continuous experience into longer events than adults. So it's just another hint that infants might be operating on this longer timescale. So could infants learn to understand the things they see in context from temporal statistics that exist in their dynamic experience? So as I mentioned, we want to look towards computational models so we can explore this idea before we even get infants into the lab. So we need a model that itself can learn from experience, pick up on the types of statistics that it sees, and build a representation of its world. We want to be able to compare this model to the brains or behavior. Importantly for my interests, because I want to test whether we could pick up a wider relational understanding from these types of statistics, we have to test the model in the right way, much like Koleen was mentioning. So we need to test with a particular metric that probes this understanding of the things that it's learned. So artificial neural networks are a really great candidate for this, and not just because I set it up nicely to tell you that. So they can do all of these things, right? They can learn themselves, they can learn in the way that we define it, and we can compare them to the brains and behavior that's quite well established in the adult literature at this stage. But it's obviously not a perfect comparison. Just to pick 2 examples, traditionally when machine learning is compared to the brain, it's when they've been trained in a supervised scenario, so everything the model has ever seen, it's been given the correct label for it, and this is just not how humans learn. Also, they classify the things they see in a very different way to humans. So they actually use texture to classify objects, and even if they're forced to classify on shape, they use the wrong types of things. So they focus on very local features that might not impact our recognition of an object, and ignore the overall global shape of the things that they see. And humans are just not doing this. So in other words, there is room for improvement. If we care about building an artificial intelligence model that mimics human intelligence, that is. And I really believe that taking inspiration from the infant literature can be hugely beneficial for building smarter models. And that's sort of the angle I've taken in this project. So I've taken an idea for learning, a learning mechanism that I got from viewing things from the infant perspective, and then tested, could an artificial neural network pick up on these things? To build a representation that captures the sorts of relations that develop a rich understanding, a relational understanding of the things it sees. So to do this, I had to build a data set that actually had these long-range temporal statistics. Traditional computer vision models just don't have this. There are millions of examples, computer vision data sets, they're just millions of examples of still images. So I focused it on movies instead. I took about 150 hours of live-action movies and generated a data set of images from these. And this will preserve the temporal relations between two images. So for example, if we have a bedroom scene and we take an image 1 second later, it's going to be essentially the exact same, to our eye anyway. But what about 1 minute later? It might be in the same room, but a different viewpoint, seeing different objects in the context. And if we take an image 5 minutes, maybe 60 minutes later in the movie data set, it will be completely different. So I thought that the objects within each of the objects across the movie dataset would be associated for a longer period of time, but I did want to quantify that. So I automatically tagged all of the objects within the movie dataset and then ran a regularized regression model, an autoregression model that tested how correlated objects were over various different time lags. And then I compared this to the low-level perceptual similarity of the movie dataset. Notice the different scales here on this plot. So the perceptual similarity actually drops off extremely quickly within 20 seconds of a lag between the two images that I was comparing. But associations between objects persisted for a really long time and longer than I even expected. They persisted for up to about 40 minutes. So long-range temporal statistics exist within this movie dataset, and they persist for much longer than the types of perceptual features that a neural network might typically pick up on. But can we actually use this to train a neural network and then train it in a self-supervised way to just automatically guide its learning on this signal? So I trained a model based on this pre-published model called contrastive multi-view coding. It was published in 2019 and originally proposed by doing contrastive learning, which learns by comparing, essentially, across two different viewpoints of the same image. In the author's case, they split an ImageNet image across two color channels and then learned by comparing these. But in my model, my two images were actually separated, two from the movie dataset, separated by a certain time lag that I defined. So these were passed through the model and then compared to a whole load of randomly selected images that were negative pairs. And the model had to learn by pushing together close pairs of images, the ones matching according to the time lag, and apart images that were just from a random time lag. And like I mentioned, we want to test this in the right way. So I used representational similarity analysis to probe the relational structure that the model learned. And then I compared it to a semantic model based off of WordNet taxonomy and structure. And what I found was that my model trained on the temporal task actually learned a more semantic representation comparing to the WordNet model, but only when there was a sufficiently long distance between the two images. So at 1 second it didn't work because the two images were basically the same and the object associations were just the same thing. But what did the model actually learn? I mean, it was motivated by all of our ideas that we discussed earlier. And to go back to our previous example, did it learn just this is a couch, or would it be able to differentiate between a couch in its expected context or it in a weird context? If we built it in this way, it should really pick up on these types of things. So once again, using representational similarity analysis and the test set provided by that second reference there, I measured the change in the network's representation when I either remove the object, which is on the x-axis, or change the background to something completely different on the y-axis. And if you look on the bottom right there, a supervised model cares a lot about removing the objects, which we expect, and not really about background. But the temporal and self-supervised networks show much more varied behavior. I think, interestingly, now these are still early results and I'm exploring them more what's really going on in the models, but at the 5 minutes it seems to care about both objects and backgrounds. And maybe as a first guess, a longer timescale could help us to form a more holistic view of the context we find ourselves in that integrates both the context and the scene and objects themselves. So I'll just quickly circle back to the neuroimaging work that we have going on. because this sounds like a plausible idea, but could it actually be in the brain? This is some work from my colleague, Dr. Anna Truzzi, and she's testing intrinsic neural timescales, so the preferred processing time of certain regions of the brain. And she, for the first time, showed that infants have consistent intrinsic neural timescales, and in general, they're actually longer than adults, at up to 8 seconds rather than the adult 5 seconds. So it's another idea that, some other evidence that infants might be operating at this longer timescale. But what about when they're actually doing something? When they're watching videos in the scanner, can we record what's happening in their brain? So that's exactly what we're doing now with our Foundations of Cognition FoundCog dataset. So this is a neuroimaging dataset. We've scanned over 200 2-month-old, or over 100, 2-month-old infants awake in the scanner who are all coming back for their 9-month scans now. So we have a lot of data here, including a clinical cohort from the neonatal intensive care unit. And these infants are watching videos and then viewing objects that are associated with each of the contexts in the videos. I'm just starting analysis on this and diving deeper into what's going on, but I've just shown here preliminary results that show we have, from an intersubject correlation, that show we have consistent visual activation across 80 infants, which is really exciting. So now it's time to go deeper into this and see what's really happening inside the infant brain. So just to summarize, I've discussed how the types of long-range statistics that exist in an environment that I think an infant might experience can be used to train a neural network, and this learned quite a different representation to one that was trained in a more typical machine learning way. And for us, it's really key that this work has provided a huge amount of inspiration and concrete things that we can test within our infant imaging data set that now we're going to continue to explore. And just zooming out a bit again, I want to touch on why I think this type of interdisciplinary dialogue is so fruitful. We all care as infant scientists about, or as developmental scientists, uncovering the hidden processes of development and understanding how human intelligence develops. And from my own experience, working with AI has really helped me in asking these questions and exploring these. But also from the AI side of things, I think looking towards infants to build better, more intelligent models might be a great source of information, inspiration for building models that are more generalizable or don't require as much expensive training data. So I think that keeping this discussion open and allowing this discussion to develop itself is really fruitful. So just thank you to everyone, and if anyone has any questions, come up to me or message me or anything.
We have time for one quick question before our discussant. Would you like to come up, Matt, and while we set up for the next talk? Any questions? Was one at one over there?
Cool. Hi, that was a great talk. I had just a sort of technical question. I was interested to know how you tagged the movie stimuli that you had.
Yeah, I actually used Amazon Recognition to tag them, and that was then those labels were only used for the regression, so those labels weren't used in the training at all. But yeah, I used Amazon Recognition just to automatically tag the movies.
Great. We will have time for more discussion in a moment. But, thank you very much, Clíona. So for our next speaker, I'd like you to welcome Matt Botvinick from DeepMind and from UCL.
Thanks very much. Yeah, it's great to be here. And I'm not here as a speaker. I'm here as a discussant. I have a few thoughts to share based on the preview I got of these three wonderful talks. But then I'm going to ask the three speakers to come up on the stage. I have questions to kick off discussion. Hopefully we'll have time for a couple more sort of general Q&A. I haven't timed this yet, so I don't really know. Is there a timer to kind of keep me on track? Yeah, just so. We have 15 minutes for the whole thing, right? Okay, so I'll try to be really quick here. Right, so thank you. Right, Right, so the one part of the title for this session was an interdisciplinary dialogue. I just have a few reflections on what that really means. So one question we can ask about that is what's under discussion in this dialogue? And I think there the answer is pretty straightforward. We're talking about computational models of children's cognition, behavior, and development, both how to build and train them. For example, that was the focus of part of Clíona's talk. But also, really importantly, how exactly to evaluate them, a topic that Shannon and Koleen concentrated on. So, but this dialogue has been going on for a long time, actually. So I did my PhD work in the late 90s in connectionist modeling, and there was, some of you may remember, there was already a lot of activity around building neural network models to address developmental data, leading to really influential work like what's reported in this book 25 years ago, amazingly, by Jeff Ellman and colleagues on rethinking innateness, and related work summarized, for example, in this paper by Yuko Munakata and James McClelland in 2003. Taking neural networks, very similar to the ones that we're training today, although generally quite a bit smaller, and applying them to behavioral, from developmental phenomena like balance scale judgments. So we've been having this dialogue for decades, is one point I want to make. But something really important has changed, and that's who's participating in this dialogue. So the old situation was we had experimental psychologists talking with computational modelers, and computational modeling really meant people deliberately building models that were intended to implement a theory of human cognition, of child cognition, or what have you. And the dialogue today is just different. We have a different participant, so to speak, which is represented by AI. AI is not these days about, as a couple of the speakers mentioned, it's not really about modeling human cognition. It's about building systems that work in certain ways, that do things that we want them to do. Those things resemble things that humans can do, but the engineers I work with at DeepMind are fascinated with human cognition, but they are just not building models of it. That's just not the game. And so we really, I think, in thinking through the structure of this dialogue, have to keep track of this distinction between AI systems as they're being developed in industry today, for example, and then computational models, which are just a very different thing, even though they have many surface characteristics in common. But if we do keep track of that distinction, I think this expansion of the dialogue really enriches it in several different ways. Oh, I was going to show you an example of an AI system that is just it's not a model of a human, but it does things that are cool. So this is something from DeepMind called Flamingo. You can show it a picture and then say, what's in this picture? And it'll say, oh, it's a bowl of soup with a monster face in it. What's the monster made out of? Oh, it's made out of vegetables. No, it's made out of a kind of fabric. Can you see what kind? Yeah, I think it's made out of woolen fabric. So these are obviously the kinds of answers you'd want a human to give, but the model is just not built in order to provide an account of human cognition. It just does stuff we want it to do, to be useful in a certain way. Here's kind of a cheeky example of why these systems look human-like, but they're really not. I don't think you'll be able to read this, but I'll read it to you. I'd like you to read the color and then say the color it is written in, for example. Purple, color is purple and is written in red. Then another, these are pictures that are being presented. So yellow, the color is yellow and it's written in green, the agent says. Another example, black is written in yellow. Great, do you know what the name of this test? Oh, it's called the Stroop test. Can you explain how humans perform this test? Humans are slower when the color of the word and the color of the word and the color of the word and the color of the word, I didn't notice that error, are different. How about you? I'm not affected by this difference, which is true. Like, this system doesn't care. It doesn't show the Stroop effect. And it doesn't matter. Like, who cares whether this thing shows the Stroop effect or not? That's not going to pay the bills. It's just not a model of human cognition. So, but it's cool, right? And the fact that it can do what it does is of interest to us as psychologists. So, so what is the structure of the dialogue now? Well, these AI systems, like the people building them, are amazingly creative, and they build things that work. And so that kind of technology development gives us all sorts of cool tools and techniques to use in building like actual computational models of cognition and brain function. You know, one example from my own group is, you know, we published this paper called Machine Theory of Mind, which overlaps with some of the work presented earlier in the session, looking at, you know, inferences in a machine learning system about what goal an agent will go to based on observations of previous behavior. But we did this work, you know, against a background of, you know, conceptual background provided by machine learning work that gave us this notion of one-shot or few-shot learning. And so, you know, the machine learning context gave us a way of kind of organizing our computational modeling to address really human-like, to build a human-like model, or at least we hope. There's a challenge here, though, because the techniques allow us to build systems that are that cover more of the ground of human behavior. So for example, you don't have to give one-hot inputs. You can give whole images. And now you have a system that has a whole perceptual system. But what if that perceptual system isn't like the human perceptual system? We already heard about how that can trip you up in trying to evaluate its other capacities. So we have these tools and techniques, but they're hard to wield. Another way in which this three-way dialogue is richer is we can see ways in which these big, impressive AI systems are still failing. And that gives us targets, right? Not because the people who build these systems are responsible for matching human behavior in every possible way, but because it's interesting to us as psychologists that these systems don't match human behavior. What does that mean? What would it take to get them to match that? For example, do these systems really have what developmental psychologists call core knowledge? Maybe AI researchers, technologists don't care, but as psychologists, it's an interesting and natural question. And you know, that's led some people in my group into work, again, very similar to work we heard about earlier in the session about kind of simulating violation of expectation setups in intuitive physics and seeing what we can get systems to do, and then drawing on insights from machine learning, like object-based segmentation, to see whether we can get systems to do better. Okay, so just to wrap this up, I don't want to use up all my time. I've already gone longer than I expected. So another complication, but an interesting one, is that we're seeing over and over again that in AI systems, if we just scale them up, they start doing things that they couldn't do before. And that's challenging. It's given deep learning, you know, what used to be called connectionist modeling, a lot more credibility than it had in my PhD days, because we've seen, it's been demonstrated that if you scale these models up and train them on a lot more data, they are much more performant. And they can generalize much better than you might have expected. But you know, how do we deal with that insight when we go to build our computational models of human cognition? How big is big enough to really draw the conclusions that we're trying to draw? And even though we're scaling these AI models up to brain level scale, they're not structured like a brain. They don't work like a brain, as I keep saying. So what does that mean for us as psychologists? Should we go try to build something just as big that is more brain-like? I don't know what the right answer is, but I think it's an important question facing us all. And of course, there are people who are building very alternative structures because they don't think that these deep learning systems are ultimately going to do what humans most importantly do. For example, Sam Gershman has this beautiful work on theory-based RL, which is just works very differently from current deep learning systems. Okay, and finally, what about development? We're training these large AI systems on huge corpora that are generated by adult human behavior, for example, texts on the internet. There's really no interest among AI researchers in getting these things to develop the way that children do. It's just a completely different way of building an intelligence than nature has chosen and that we are interested in as psychologists. What do we do with that? Does this mean we can't draw any conclusions from these pre-trained systems? And with that particular question, I want to now pivot to my own questions for the speakers. So if I could ask the speakers to come up on stage. I have a question for each of you, and I'm a little bit worried that that's going to use up all our time, but if we have any left, we can throw it open. Thanks. Okay, so Koleen, if I could start with you. So yeah, I was just making this point about development. And so my question for you is, choosing the training set or the training distribution turned out to be contentious in your multi-investigator setup. How does that choice relate back, though, to developmental psychology? So specifically, how should we think about the training set in the context of child development? And especially, this is something that I always get stuck on, especially given that evolutionary processes make the relevant experiences or data of previous generations relevant, even those of adult ancestors. So I'm curious how you think about that.
That part was so sticky in this project. So I think ultimately what has ended up happening is that we're counting on the programmers to give the AIs the things that we got from evolution. And then we're counting on the AIs to get the things that we can't get from evolution in the ILE, right? Because, yeah, and it's very, very hard even to really think about training in a human system, because there are some people who say, oh, well, even in the womb, we're getting so much rich information and feedback, right? So what's the time scale of training? Is it 40 minutes? Is it 5 minutes? Is it 1 second? Is it a millisecond? Is it this time span of a neuron firing? Is every neuron that fires a little zzz of training? So I think, I'm sure I don't have a great answer for your question, but I think it is a central part of developing AI that you have to bust in there as a human and give the systems guiding principles like evolution has given us guiding principles that we're starting off with.
Thanks. It makes a lot of sense. Let's power on because I want to try to get to everybody. But thanks for those insights. Okay, so Clíona, if I could turn to you. Your talk highlighted the potential importance of distributional structure in the training data that children encounter. Are there any lessons here for current AI systems, like the ones that are being developed in industry? We're training language models on large text corpora, and soon we'll be seeing the same techniques increasingly applied to video corpora, and, for example, YouTube. These presumably have distributional structure quite different from what's encountered spontaneously by humans, or at least children, in naturalistic settings. So what are the consequences likely to be, and can we do better than that?
Yeah, I think it's a really important question for multiple different reasons. One that I always think of in terms of getting the distribution in a training set right is in terms of ethical AI and fairness and things like that. I mean, we know that we're failing a lot of the time in that regard and with a lot of the models. It's also, do we want our model to learn some of the crazy things that are on YouTube? You know, so I think it has been ignored until recently, and just talking about it really makes such a difference and lets us think about what exactly the models are learning. But then I think it also goes back to what the goal is here, which you touched on and Koleen touched on as well. Do we just want the model to do the task, or do we want it to learn something that is, do we care about how it's doing it? So I'm not sure in terms of the goals of industry if they just want to build better recommendations for the consumer or things like that, whether considering a realistic distribution matters for those purposes. But I think the glaring thing for me is in terms of ethics and fair AI, because that is relevant for everyone.
Yeah, thanks so much. Makes perfect sense. Okay, so we do have a few seconds left. Hopefully we can go over and give Shannon a chance to give a full answer to this question. So getting deep learning models to robustly show quote-unquote core abilities that we attribute to children appears still to be tricky, especially in multimodal environments. So do you think that there are fixes available specifically for deep learning, or is deep learning fundamentally flawed, as has long been suggested by some in the research community? And if the latter, what's a more promising path?
Yeah, that's interesting. So we've had people actually work on finding solutions for BIB, and the more symbolic approaches seem to be more successful. But we have had some more successes with better successes with deep learning models as well that use just like transformer video transformers. I don't have I think that's something that people who are working on these problems are still exploring. Do we want these purely data-driven approaches? Most likely it's something in between. There still has to be some. If we want it to be especially flexible, then we want it to be able to learn from given just data. But there's likely some things that need to be built in, just like there are with us.
The wisdom from evolution.
Yes, exactly.
In some form, right? Great. Okay, I guess we are out of time. Is that correct? Okay. Well, maybe we can take one question from the audience then.
Oh, there it goes.
Hi. Thank you so much for the discussion. Thank all the speakers. And actually, I think I have a question for you, and that is the how you presented sort of what the role of AI and sort of the interdisciplinary debate or dialogue that is going on. And I wonder if the push that we are seeing here from these three researchers here is that AI is having to interact with humans more than maybe it had to in the past, and therefore even if AI is not simulating how humans think, it has to know what humans think and how humans think. So it has to know how to respond to humans. And then the question is, can it do it in a way that it's not the human way to respond?
Right, right. As you talk, I'm trying to pull it. I'm not going to manage to do it. I was going to try to pull up this paper that I just published in Trends in Cognitive Sciences, talking about new roles that cognitive science can play vis-a-vis AI, and a lot of the article is specifically about this, right? You know, one reason that I'm excited about the direction that AI research is going in industry is that it is centering more and more on human interaction, partly because of the recent breakthroughs in natural language processing, but more broadly, you know, ultimately, companies like Google want this stuff to be, you know, deployable, right? Like, it's not a research project, it's technology. And that means it has to, at some point, interact with humans. And yes, I think the point that you're making is absolutely central. It really doesn't, even if these systems aren't human-like themselves, in order to interact effectively and most helpfully with humans, they have to understand humans, which amounts almost to the same thing, right? Because they have to have an internal model of how humans, and there are all sorts of interesting complexities there. For example, they have to understand all of behavioral economics, right? You know, they have to understand, you know, the way that human preferences change over time and so forth. Yes, and I think that is a way, and I'm glad you brought this up, because I think that is, I should have put it in my own spiel. This is a way in which psychological insights are going to circle back to being really relevant to AI. And just as a closing note, just to show you that I really mean it, we just hired a developmental psychologist out of MIT into my group, specifically to work on human data for training AI systems, to try to get that kind of perspective into the research cycle for developing human interactive systems. Yeah, totally agree. Great, okay. I just want to end by thanking the speakers again for a fascinating session.